Hi there. In this video we're going to talk about discrete subgroups, Friezes, and Tilings. So we're going to start off with planar isometries, then get into the notion of discrete groups, Friezes, Tilings, and we'll finish off with the Fedorov geometries. Let's get started. So planar isometries are maps of the plane to itself that preserve the Euclidean distance on the plane. So these are the length-preserving transformations of the plane. We write sim of R for the group of isometries of the plane, and it includes translations, rotations, and glide reflections. So we can either translate, we can rotate, or we can translate and then reflect. Okay, so a glide reflection combines the notion of translating and reflecting to get a map of the plane. We also have the subgroup of orientation-preserving isometries of the plane. So this includes translations and rotations. So if we want to preserve the notion of left and right, then we have to either be a translation or a rotation. All reflections are orientation reversing. Now let's get into the notion of a discrete subgroup. So this is a definition that comes from topology, and it has to do with the idea of limit points and accumulation points. So if you haven't taken a topology course, we're just going to give you an intuition for how this works. We say that a group action is discrete if the orbits do not have any limit points. So that is to say, when we look at an orbit, all of the points are sort of far apart. They don't bunch up and collect together anywhere. So let's have a look at an example of this phenomenon. We're going to consider the notion of the integers with addition acting on the point x0. So we'll draw our number line. We'll label the point 0. And now when the integers act by addition, we're translating over by integer amounts. So 0 goes to 1, 1 goes to 2, right? And we can also go the other way. -1 goes to 0, -2 goes to -1. Right, so here we get discrete points that are all well separated. And if we calculate the orbit of the point 0 under this group action, we get all of the integers, right? We get the collection of points with integer values. And this set doesn't have any limit points inside itself, right? It's very, very discrete. There's no point that is surrounded by infinitely many other points. So we would say that this is a discrete action. Okay. Now let's look at an action that's not discrete. Consider the rationals acting on the point x equals 1. So here we'll start off with our number line. And we can move that point 1 anywhere we want as long as we move it to a rational point, right? So we could move it in principle to a half, to a third, to a quarter, right? So we can add rationals that get this closer and closer to 0. So the orbit of 1 is going to be all of the rational numbers. And in particular, we're going to have the rational numbers a half, a third, a quarter, a fifth inside our orbit. And we know that the limit of 1 over n is 0. Right? So these orbits all collect around the point x equals 0. They sort of clump up there. In fact, the closure of the rationals is the real. So this orbit, it clumps up not just at 0, it actually clumps up at every single point in the real numbers. So this is a group action which is not discrete. Okay, because the orbits get very, very close to lots of different points. All right, so how do we use this notion? Well, we could ask about the action of the symmetry group on R2 being discrete. So take a moment and think about this before proceeding. Feel free to pause and try and do some calculations on your own before watching the next bit. Okay, suppose that we've got the plane. And we pick some point like 1, 0. Right? We can now use any isometry of the plane to move this around. So we could move it, say, up a little bit. Right? We could move it towards the point 1, 1. In fact, we could translate it by any amount we want. So we can translate to the point 1, 1 minus 1 over n for any n. Right, so we have a sequence of points that's going to get closer and closer to 1, 1. Right, so we know the limit of 1, 1 over 1 minus n is 1, 1. So we see that these are collecting up at 1, 1. And there's many, many other places where in the orbit where this limits to. For example, we might consider rotating, right? And we could rotate this to infinitely many points that accumulate at the point 0, negative 1, for example. Right, so this has many, many limit points or many, many accumulation points. So this action is not discrete. Okay, let's do one more example before moving on. Is the action of z squared on R2 discrete? Again, I encourage you to take a moment and pause and think about this for yourself. So how does z squared act? Z squared is the collection of points with integer coefficients. Right? And it acts in the following way. So KL acting on the point xy. Right? So remember, we've got our group element on the right and our point on the left. This action is going to be x plus k, y plus l. So this group acts by translations on points in R squared. And if we imagine what this does to, say, the origin, right, we've got the origin here. if we look at the orbit under this group action of the origin, we want to look at all of the places that z squared sends it. So we can translate over by a unit, up by a unit, or we can translate over and up by a unit at the same time. So what we obtain under all of these translations is this sort of lattice shape, and we wind up looking at all of the points with integer coefficients. Right? So this lattice is really well separated, it's well spaced out, and we wind up obtaining that this is a discrete group action. Okay, now let's get into how we use this notion of a discrete group action to look at symmetry. Consider the following thing called a frieze. A frieze is a pattern in R cross an interval, right? So it's a pattern in a strip that continues indefinitely in both directions. So here's our copy of R, here's our interval, and we have some kind of repeated motif in that pattern. Here, we've got these feet, and we're going to look at the symmetry of these feet as a group. So let's pay attention to what each foot is doing here. We've got two different symmetries in this pattern. We've got a translation symmetry, T, and we also have a glide reflection. We can translate along and reflect at the same time. So this is a glide reflection that relates the left-hand foot and the right-hand foot. Now, we want to figure out what is the group of transformations that preserves this frieze? What is the pattern that the symmetry encodes for us? So our group is going to be generated by two elements, T and G, and we want to see what relationships those generators have. So one thing that we can note is that if we apply G and then apply G again, then we go left, right, left. And that has the same effect as translating. So we wind up with the relationship that G squared is equal to T. So I want to point out something about this group. If we're looking at words that are composed of T's and G's, and we know that T can always be expressed as G squared, then we don't really need any of the T's at all. The T's are sort of redundant. So this group is actually just generated by the glide reflection G, and that glide reflection doesn't satisfy any relationships. So this group is all of the powers of G, and we wind up getting that the symmetry group of this pattern is the same as the integers. So let's take a moment to kind of interpret what this means. If we call this the 0th footstep, right? Let's suppose that that's our sort of fundamental first footstep, right? Then the symmetry that we care about is just the identity, right? The identity leaves that footstep in place. Now let's apply one of these G's. Then we'll get to this footstep at T equals 1. Then the symmetry that carries us there, as we can see by this label G, is just one copy of G. How do we get to this next footstep? Well, we apply G twice. We apply one copy of the glide reflection, followed by another copy of the glide reflection, and we wind up with this at g squared. So the symmetry that carries t0 to t2 is applying the glide reflection twice. How do we get back to this footstep just before t equals 0? Well, we would take one step backwards in our pattern. To take one step backwards and to get to t equals -1, we apply the inverse of g. So we apply g inverse here. Right? So this establishes a correspondence between the integers and the footsteps. Right? To get to any footstep, we apply the glide reflection so many times, and we get to a point in our path. So this is sort of giving a physical interpretation or a algebraic interpretation of this footsteps in the sand pattern. Okay, let's move on to the notion of tilings. A tiling, or tessellation of the plane by a polygon T0, is a decomposition of the plane into infinitely many copies of the proto-tile, or the tile T0. So we start off with a single tile T0, and we split up the plane into infinitely many copies of that proto-tile T0. So given such a setup, we can rewrite r squared as the union over all of those tiles that are all congruent to T0. Okay, now let's look at the notion of a regular tiling. A regular tiling is the same kind of thing as a tiling, but it's got just a little bit more structure to it. We say that a tiling is regular if there is a group of symmetries and a tile such that the group of symmetries moves that tiling around for us. So what do we need? We need the group G to act discretely on r squared. We need that the orbit of T0 fills the plane. And we need that the group action is transitive. So what does the condition transitive mean for a group action? We need that if two group elements, G and H, give the same tile in our tiling, then G and H had to be the same group element of the group G. So this is sort of saying that our group action is not redundant in any way. Every G takes us to a different place in the tiling. Okay, we say that this space, together with the transformation group G, is a Fedorov geometry, or alternatively, a tiling geometry. So our space is r squared, and the group G of transformations is the way of moving throughout the tiling according to our group. If we have a group of transformations that's orientation preserving, so that every element is either a rotation or a translation, then we call this a one-sided Fedorov tiling. So that is to say, it's sort of monohedral. Every tile can be obtained as a translation or rotation of one tile, and we never need to turn the tile over to do so. Okay, let's have a look at a couple one-sided Fedorov tilings. Here are two examples from our textbook. We're going to look at this first one in this video, and we'll come back to the second one in class. So as we can see, we have a repeated unit. So here's our proto-tile T0. And now we want to look at the transformations of this tiling geometry that allow us to move that tile around. So we notice that there's a translation in the y direction, and there's also a translation in the x direction. So we've got that this tiling is generated by these two translations, one vertically and one horizontally. So we can say that our group is generated by x and y. And now we want to figure out what relationships these generators satisfy. So we want to look at what happens if we perform xy and yx. Okay, so let's first examine what happens if we perform xy. We translate a point from here onto the tip of x, and then we translate up according to y and get here. Right, so we sort of go right and then up. All right, now let's see what happens if we go y then x. If we go y, we translate here, and then x we get here as well. So what we've noticed is that these two orders agree, right? If we apply xy, we get to the exact same point as if we apply yx. So what this is telling us is that these commute. So if we think about the elements of this group, we can always rearrange the x's and y's in whatever order we want. So we're going to get x to the k, y to the l for k and l in the integers. And if we think about that as an abstract group, that's going to be z squared. So the group of transformations preserving this one-sided tiling is exactly the integers squared. Okay, notice that in our second tiling, we have a little bit more structure. We also have a rotation here by 120 degrees. Or sorry, 180 degrees. Okay, so we're going to talk about how to deal with rotational symmetry in class. Okay, I would like to end off with one last tiling. This is a bit of a mysterious tiling. I drew it, and I want to take you through a little bit of the structure inside this tiling. So notice that we have 6-fold rotational axes. And if we look at the axes of symmetry, we notice that there's also a reflection across those lines. Right, so we have a reflection symmetry that takes this branch onto this branch here. Okay, so this is an example of a tiling that has some reflections in it. So we obtain that G is not a subgroup of the orientation preserving transformations of the plane. Okay, so we say that this is a two-sided tiling. Okay, because in effect, we need to turn those tiles over to get that reflection symmetry. Excellent. Thank you for watching.